Alright, so we're going to talk about the integral test today, the second test for convergence and divergence, okay? We're going to kind of explore some concepts before we jump straight into the test, cool? So, I want you to take a look at f of x equals to 1 over x from 1 to infinity, okay? So, we're going to take a look at that function. What I want to do with this function is that I actually want to take an integral from 1 to infinity. I'll explain to you why we're doing this here in just a second. This shouldn't be that difficult for us. We got an improper integral. An improper integral is when one of our boundaries, our limits here, is infinity, right? So how do I take care of that? Yes, sir. Cool. Substitute it with a variable and take a limit, right? So we're going to take the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. You guys recall doing this? So you should not struggle with what is the integral of 1 over x. Cool. So we're going to take the limit as b approaches infinity of natural log of x evaluated from 1 to b. Correct? Which then becomes what? The limit as b approaches infinity of natural log of b minus natural log of 1. You guys agree? You with me? What's the natural log of 1? So that's gone, right? Agreed? So literally I'm just left with what's the limit as b approaches infinity of natural log of b? Infinity. You guys agree? Yeah. Now, if we were to look at this as the concept of area, we do have a definite integral, right? It's like basically saying that underneath the graph of 1 over x, if I were to go to infinity, I'm never going to really finish an area. It's going to go to infinity. You with me? Yes? Okay. Now, I'm going to try to relate this to series. And the only way that I can think of doing that is by going back to Riemann Sums. So I'm going to use the very same example, and we're going to do a Riemann Sums instead of an integration. You with me? So I'm going to do a Riemann Sums, and I'm going to grab this in order for you to see it. So we have the function f of x equals 1 over x. But since we only care about, we're going to make this into a series, right? So I'll need a sequence. And sequence have what type of domain? Positive integers. So I don't really care about anything on the negatives. So I'm going to start at 1. So at 1, do you guys agree that I would be at 1? Yes? And then at 2, where would I be at? 1/2. At 3, 1/3, and so on. You guys, you're with me? So it goes something like that. Just continues to go down. Cool? Alright. What I'm going to do is I am going to use a left-handed Riemann sum. Do you remember what that means? The height of the rectangle is it's represented by the left side. And I'm going to start where? 1, because that 2 is the right, 1 is the left. Agreed? So 1 would be the height. And I want this rectangle to have a width of 1. So I'm going to go from 1 to 2. You with me? And then from 2 to 3. And then from 3 to 4. And I think that's enough for you to understand what I'm doing here. Yes, ma'am?
How come you connected the dots?
Because I'm using the function, and I'm eventually going to tie it into a series. Okay, so right now we are dealing with a function, so that is why I connected the dots. You with me? Okay, question. You remember that through integration we get an exact answer per se, right? Through Riemann sums we get an approximation. Agreed? Would you say that my approximation is more or less than the actual area? More. This is an overestimation. You guys agree? Because I have all these little extra parts on each one of these rectangles. You with me? So here's what I want to do. Would you then say that the area is approximately, and look how I'm going to write this. You ready? I'm going to take each rectangle and add it together. The width of the first rectangle is 1. And what's the height? 1. Plus, the width of the second rectangle is 1. And what's the height? 1/2. Plus, the width is 1, and then the height is 1/3, and this goes on forever. Yes? You with me? Isn't technically then the area approximately 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 ... And that looks like a sequence to me that I can turn into a series. So could I say then that the area is approximately the series starting at 1 and going to infinity of what? 1 over n. Right? Because if you plug in 1, you get 1. If you plug in 2, you get 1/2. You plug in 3, you get 1/3. You guys agree? Alright. I want to make sure I don't lose you. We started out with a function, and through all the work we're doing, I now brought it to what we're doing, which is the whole concept of a series. You with me? Okay. Now I'm going to make a connection between this and what we did earlier up here. Okay? Here's what you do know. The area is approximately the series from 1 to infinity of 1 over n, right? Now, you told me, according to the sketch, so that you visually see it, that this is an overestimation of the actual area, right? So this is more. So this is more than the actual area. The actual area was that. Agreed? So here's my question. Let's make a conclusion out of this. If the area is approximately this series, and this series is more than this, what can you tell me about the series? It's divergent. Why would it be divergent? Because it's got to be bigger than infinity. I'm going to repeat that one more time. If the area is approximately this series, right? And this series is bigger than the area underneath this function. If this function is going to infinity, and this series is going to be bigger than infinity, what can you tell me about the series? It's divergent. Therefore, since this series has to be bigger than infinity, the series diverges. Are you okay with what I did here? All I did was, I want to be honest, this is what I cared about, but I started by making it into a function. Do you remember how earlier when we started the chapter I was like, hey, let's just pretend we have a function because we can do more things with the function? It's kind of the same idea. I made it into a function so eventually I could relate it to what we're doing. Okay? We're going to do one more example so I can show you how this can work another way, and then we're going to make a rule based out of that. Okay? Yes, sir. No. I'm about to give you another one. Okay? Cool? Now, what we're doing right here is like later on you don't want to do it this way, right? This is the long way. We're going to develop a rule based on this. We're going to make some observations. Okay? Any questions on this one before we move on to like our second example? Yes. It doesn't. 1 over x is 1 plus 1/2 plus 1/3 plus 1/4. So your question is like, and I know what you're saying. Well, if I reason this out, the numbers are getting smaller, so I should eventually be reaching something. Is that your reasoning here? Yeah. But I just proved to you, like through like the use of math, that it's not going to happen. And that's why when like earlier when you took the quiz, that's why it's flawed to think, and that's why we have all these tests, that just because something gets smaller necessarily will reach a number. That won't always be the case, and I just showed you an example when it won't. Okay? So, from now on, that's why we're investigating all these tests. You're no longer going to try to reason things out because you're not going to say, well, this is getting smaller and smaller, so therefore it's going to converge. It's not going to be good enough reasoning. Okay? We're going to have better tests that you can tell me for sure this thing is going to converge because of this. This thing is going to be divergent because of that. Okay? Yes, ma'am. Well, the whole idea is that if you're already in infinity, and your infinity is not per se a number, right? So it just means like it's a bigger number than whatever that was, if we were to consider it as a number. So if it's already at infinity and it's bigger than that, that means that it's just, it really like, just pretend it's infinity per se. See what I'm saying? Okay. All right. We're going to do the exact same thing. All I'm going to do is change it to this. We're going to do the exact same thing. What's the difference? Very similar function. What's the only difference? It's got a power on the denominator, right? Higher than 1. Cool? Alright. Integral from 1 to infinity of 1 over x squared dx. We're going to take the limit as b approaches infinity of the integral from 1 to b, and I'm going to rewrite it just to help you out a little bit, x to the negative 2 dx. Right? You okay with that? Okay, what happens when I integrate this? Negative 1 over x. You guys agree? Cool. So then this becomes the limit as b approaches infinity of negative 1 over x from 1 to b. Yes? The limit as b approaches infinity of negative 1 over b plus 1 over 1. Do you understand why I turned into a plus? Yes? Okay. What's this limit equal to? 1. Why 1? Because technically this goes to 0 and then this is a plus 1, so it's 1, right? Interesting. We actually reached the value. On our previous example, we went to infinity. On this example, if we're talking about area, the area is actually 1. You're with me? Yes? I'm going to refer this once again to a Riemann sum. Okay? That's where I'm going with it. Yeah. So now I'm going to use a Riemann sum. But look, what I'm going to do is I'm going to do the same thing we did on the previous example, where I'm going to use a Riemann sum. I'm going to kind of graph this f of x equals 1 over x squared. And then we're going to make some conclusions by making it into a series, right? So once again, if I plug in 1, I'm at 1, right? But now if I plug in 2, you are at 1/4, right? And then it just gets smaller from there. Agreed? So it still kind of looks similar to the first one, but do you notice how the drop is more drastic per se? Yes? Now, here's the trick in order for you to see this one. Instead of doing a left-handed Riemann sum, I'm going to do a right-handed Riemann sum. I'll explain to you why here in just a second. I still want the width to be 1. So if I'm going to use a right-handed, that means I'm going to go at 2 and I'm going to make the height and then go to this direction. Okay? And then it's going to be hard to see because I drew it very small, but do you guys see how I'm going to be underneath this time? So what does that mean about the estimation? It's an underestimate. Okay? So then we can say the following, using the Riemann sum. The area is approximately, notice how I'm still using a width of 1, right? So it will be the width times the height. What's the height of the first rectangle? 1/4. Plus, what's the height of the second rectangle? And the third one? And so on, right? Could I then say that the area is approximately, can I go ahead and just turn it straight into a series? A series from, and look at this, I'm going to start at 2 to make it easier. Why would I make it a 2? Cool. Yes? Of what? 1 over n squared? Right? So because if I start at 2, that would be 4. And then 9. And then 6. Do you see where I'm going with this? Yes? Okay. I am going now to relate this versus what we did earlier. Okay? So the area is approximately this series right here. Agreed? Yes? And you guys told me that this is an underestimation, right? So it's actually less than the area. Agreed? So this is going to be less than this integral. And what was the equivalent of that integral? 1. So if this is less than 1, what can you tell me about the series? It's convergent. Why would it be convergent? It's going to actually reach a value. You with me? So it's not going to be 1. It's going to be less than 1, but it's actually going to reach a value. Therefore, since the series from 2 to infinity is less than it converges. Cool? Now let me explain to you, because the question typically that I get is like, what made you decide to do a right-handed sum versus a left-handed sum? If I were to do a left-handed sum, do you see how I would still get an overestimate? That would mean that that's greater than 1. That doesn't tell me anything. If it's greater than 1, it could still reach a number, but it could still go to infinity. You with me? The reason why I chose to do it on the first example is because the result was infinity. So if it was bigger than infinity, then that guaranteed me that if it's bigger than infinity, it's gonna be like a bigger infinity, which makes it divergent, right? But if I were to do that here, all it would tell me is that it's bigger than 1. And that's not enough for me to say, well, that's gonna be divergent. That's the reason why I chose to do a right-handed, so that I can show you that it's an underestimation, and I can show you this proof. You with me? Yes, sir. If I do a right Riemann sum on the first one, I'm going to get under, right? And if it says that it's under infinity, that doesn't guarantee you anything. It could still be some form of infinity. You see what I'm saying? So I chose examples that would guarantee it, and that's the reason why I made the decisions that I made. Okay? Yes?
So it depends on the interval. If the interval equals infinity, you do less. If the interval equals any other number, like an actual number, you do less.
Correct. Now, let me make sure that you guys understand what's going to happen. I'm not going to ask you to do all this. We're going to make a rule out of this so that you don't have to be thinking like, wait, do I do a left-handed or right-handed? You don't want to be doing this. This will take forever, right? So we're going to make a rule out of this. Okay? And that's called the integral test. Do you notice how we've been doing integration? The integral test says the following. Okay? Ready? Go ahead and post it up so that you guys can write it. I know it's a little small. Let me zoom in. And that's the best I can do so that you can fit the screen. Alright, so the integral test says the following. Okay? Suppose that you have a function. And this is very important. Okay? It has to be continuous. Did you notice that the examples that we did were continuous? They have to be positive. Did you notice that the examples that we did were all above the x-axis? And they have to be decreasing. Did you notice that the two examples that we did were decreasing? Okay? It has to meet those requirements. If it fails any of those, then this test is not going to work. Okay? So if it meets those requirements, then the following is true. If the integral from k to infinity of the function is convergent, what that means is that if it actually reaches a number, then what can you tell me about a series? The series will also be convergent. Number 2 would be the opposite. If the integral of that function diverges, then that series would diverge. Okay? While you're writing this down, I want to make sure that you understand something. So actually, let me give you a minute for you to write it down because this is very important. So I'm going to go ahead and pause the video and let my class write all this definition down. Okay. Last class we spoke about geometric series and we spoke about telescoping series. On a geometric series, you were able to tell me like, hey, not only does it converge, but it converges to this value because you know a formula, right? Same idea with the telescoping. Things would cancel out, you would add them up, and you're like, okay, it converges and it converges to this. Okay? For the integral test, I know you're going to get a number out of it, right? So, because in order for this to converge, the integral has to converge to a number, right? That number is not the solution of the series. You cannot tell me that the series converges to that number. All that the integral test tells you is that it does converge, but it doesn't tell you to what. Okay? So this is important. This test does not give the value of the series. It simply states if it diverges or it converges. Do we understand that? So please don't write down, like for example, if the integral goes to 5, don't say that the series converges to 5. The series converges, period. Cool? Questions about the integral test? Because we're only going to do one example, since we've already kind of done 2. You with me? All right. Then let's do it. We're going to determine the convergence or divergence of the following series. We have a series from 2 to infinity of the natural log of n over n to the 4th power. Okay? Alright, the very first thing we're going to do is, I know that we're talking about the integral test, but after you finish this chapter, you're going to know a whole bunch of tests, and you're going to have to know which one to apply. What I always recommend, you should always use the Nth Term Test first. Why? Because if it passes the Nth Term Test, you're done. You with me? So let's apply it here. The limit as n approaches infinity of the natural log of n over n to the 4th gives you what? Infinity over infinity. So L'Hopital's. Limit as n approaches infinity. What's the derivative of natural log of n? 1 over n. And the derivative of n to the 4th is 3n cubed, which is really 1 over 3n to the 4th, right? I'm sorry, 4n cubed, sorry. So it's 4n to the 4th, right? Yes? What's the limit of that? 0. Remember, the Nth Term Test says what? If it does not equal to 0, it's divergent. So in this case, it did not help. We're going to have to go somewhere else, all right? So what we know at this point, it's still, it could diverge, it could converge. So we still it really didn't help much. You with me? Now the only other test that you know as of today is the integral test. So that's where we're going to go next. Well, we need to check some requirements. First of all, we're going to make it into a function. So f of x equals to natural log of x over x to the 4th. First thing we need to check. Is this thing positive? Yes, because we're only going to be plugging in positive numbers, right? That will be positive no matter what I plug in. That will be positive. Positive over positive is positive. Yes? Number 2, is it continuous on the domain that we need it for, which is just the positive integers? Yes. There's nothing you need to do to be checking this, but you do have to communicate to me on your paper that you've checked for this. Cool? What's the next requirement? Decreasing. This is where you are going to have to use some calculus. How can you prove that something is decreasing? The first derivative test. So, you know that f of x is this. Yes? I need to find the first derivative. What's the derivative of that? So, we can either use quotient rule or we can use product rule. It's up to you. What do you want to go? Quotient? Alright, so it's x to the 4th times what? 1 over x minus what? ln x times 4x cubed over, technically, x to the 8, right? Okay, so there's the first derivative. What are we trying to do? First derivative test. So I got to find the critical numbers and then test them out, right? How do I find the critical numbers? Set it equal to 0, and also include what else? Asymptotes. Where is your asymptote? 0. It's not really going to affect us, though, because we only care about the positive integers, right? But my number line is going to start at 0, just for the sake of what we're doing. You with me? Okay. We're going to set this equal to 0. You with me? So I'm going to simplify a few things. So this is x to the third, right? And then this becomes minus ln x 4x to the third, and I'm going to set that equal to 0. What do you guys notice? Well, they both have an x to the third, right? So I can factor it out. Then I would have 1 minus, technically 4 ln x equals to 0, right? X equals 0, we already have it there, right? So now we just got to set this equal to 0. You with me? So that means I have ln x is equal to negative 1/4. Yes? Because I'm actually positive, right? Because I'm going to subtract and divide. Yes? So what is x? e to the 1/4. Very good. So that is going to be a critical number. Yes, ma'am?
Could you say that because of the horizontal axis at 0 that it will?
Yes. Yes. So let's say we were to go in this direction with the first derivative test. We get that, right? Remember how I said that I don't really care what happens at the beginning. I just care about what happens after that? I'm going to ignore this. I'm just going to plug in a number after this. I'm going to choose a number that's very easy. I'm going to use e for what we're dealing with. Because if I plug in e, do you guys agree that if I plug in e right here, that would be just 1? And then, do you guys notice how this would be x to the third? And then this would be minus 1, and then it's 4x to the third. You see how they both have an x to the third? It's going to be the same number, but this one's going to be bigger because of the 4. So when I subtract, it's going to be negative. So what does the first derivative test tell you? It's decreasing. We're good? All of that so that we can do what? The integral. Now what can we do? We're going to do the integral. So we're going to say the limit as b approaches infinity of the integral from where to where and why? 2 to infinity. Why 2 to infinity? Because n equals 2. Let's go back to, right? Okay, from 2 to infinity. You with me? Of what? ln x over x to the 4th dx. Now I chose this problem so that we can review. Our AP exam is right around the corner, so we got to review some stuff. I'm not going to give you any integration. This is going to be integration by parts. Of course. We're going to rewrite this so maybe you can see it as x to the negative 4 times natural log of x dx. And if you try use substitution, it's not going to work. Any of the other strategies that we've done in the past, it's not going to work. So your last resort is not cry. Well, I mean, you can always cry. I'm not going to stop you. We're going to do integration by parts. So Liate. Logarithms first, right? We do have a logarithm. So that means u is ln x, and dv is going to be x to the negative 4 dx, right? Okay, what's du? 1 over x dx. And what is v? Well, what's the integral of x to the negative 4?
Negative 1/3 x to the negative 3.
So we add 1 first, so that's x to the negative 3, right? And we divide by that, so that will be negative 1/3 x to the 3rd. Yes? Okay, I ran out of space, so let me kind of move. Alright, so that's where we're at. What do you do from there? I don't know what that means. I'm sorry.
Minus integral of VDU.
So we're still doing the limit of u times b, so negative natural log of x over 3x to the third, minus the integral, but because this is a definite integral, don't forget that you need to include your limits there, of what? V du.
Can you make it plus?
I know, hold on, man. Gotcha. Okay. So this and this together will become a negative 1 over 3x to the fourth dx. Shouldn't that be what? I'm sorry, what? Oh, I'm sorry, yes. Good catch. 2 to b. Thank you. All right. We can take out this negative and this becomes a positive. So then this becomes the limit. Now, I made an observation that hopefully you've made that observation as well. You're going to have to take the integral of technically 3x to the negative 4. Well, I can also pull out the 1/3. Do you guys remember that? And then technically you got to take the integral from 2 to b of x to the negative 4 dx. And I really like seeing that because I've already done it. I mean 1/3. Thank you. Right, because there was a 3 here. So I pulled out a 1/3. I like what I see here because I've already done it. Where did I do it? Over here. Remember? So I know the answer to this already. So the limit as b approaches infinity of negative natural log of x over 3x to the third. Now the integral of this is negative 1/3 x to the third, right? Times positive 1/3, it becomes what? So minus 1 over 9 x to the third. Yes? From where to where? 2 to b. Yes? Woo. Alright, so now it is the limit as b approaches infinity, and we're going to plug in our limits there. So negative natural log of b over 3b to the third. Was it 3b to the yeah, it is, right? Okay. Minus 1 over 9b to the third. Yeah, once I integrated, it became negative. And then minus negative natural log of 2 over, what's 2 to the third power? Times 3? 24. Minus 1 over 2 to the third power is 8 times 9? 72. Okay. What's up?
Why do you have to like write it all out? What? Can't you just do that since it's plugging in infinity? Like limit as opposed to infinity? So 1 over x cubed, 1 over x cubed, both of them turn into 0.
I agree. I'm just showing my work. That's all I'm doing. Okay. Now, all I did was write the entire statement. You with me? I haven't taken the limit. Yes? Yes, sir. Okay. When we start plugging in infinity, do you agree that this is going to give you natural log of infinity is just infinity over infinity? So I'm going to have to use L'Hopital's here. Yes? Now this would just become a 0. So that's kind of gone, right? And this is a number. I don't know what it is, but it's a number, right? So I'm going to approach that number, whatever that is. Yes? Okay. I'm going to apply L'Hopital's here. The limit as b approaches infinity. What is the derivative of negative natural log of b?
Negative 1 over x.
1 over b. And what's the derivative of 3b to the third? 9b squared, which technically becomes the limit as b approaches infinity of negative 1 over 9b cubed. What happens to that? It goes to 0. So if I summarize things, this goes to 0, right? We already say that the limit for this went to 0. And then this goes there, right? Whatever that is. I don't need to know what it is. It is an actual value, right? So what can you tell me about the series? Therefore, the series from 2 to infinity of ln of n over n to the fourth converges by the integral test. you have to mention by what test it's converging or diverging. Okay? Can I do what? Sure.
It was like really fast. I'm still working on the integration.
All right. That's what the integral test does. So I think one example gets the point across. You'll be able to practice this on your own and when you do the homework. But that really actually takes us to another test. And I want you to observe something. On the very first two examples that we did you notice that the first one was divergent? And that was 1 over x to the first power. And then the second one converged, and that was 1 over x squared. What do you think about x to the third? It'll be convergent. And I want to talk about that real quick. And I kind of mentioned this. I dropped this while we were talking to see if you would understand it. I kind of mentioned this. Did you notice how it started dropping faster, decreasing a lot faster? After that, think about it. The higher the power is going to even decrease even faster and faster and faster. It's going to converge. That right there is called the P-series test. And this is the easiest of them all, and you're going to like this test. The P-series test. If k is greater than 0, then the series from k to infinity of 1 over np converges if p is greater than 1, and diverges if p is less than or equal to 1. And it's so easy to apply. So easy. Let's say we have a series from 1 to infinity of 1 over n to the 7th power. Convergent or divergent, and why? Convergent, why? P is greater than 1. Therefore, converge. That's simple. This is one of the easiest tests you're going to run into. Cool? One more. The series from 1 to infinity of 1 over the square root of n. Convergent or divergent? Why?
Because
P is 1/2, which is less than or equal to 1. Therefore, divergent. Have a fantastic weekend, guys.